All right, so the last topic that we're going to go over is what's called synthetic chemistry, and it's essentially working the exact opposite direction of what we did in the last lecture, right? The last lecture was all about, given a reagent and a substrate, can I predict the products? For synthetic chemistry, the goal is, I have this thing that I want to make, how do I get there, okay? The approach that we use here is what's called a retrosynthetic analysis, which is a big fancy way of saying working backwards, okay? Meaning you're going to look at what you're trying to make and then consider how you get there, which might sound like a pretty obvious approach because that's how we do a lot of things. Like, so in this slide, it points out the example of like building a house or building anything really, right? You have in mind what you're trying to make and then you figure out how to get there. Importantly, you don't just sit down and start putting down chemicals on the page and turning something into something else and hoping you get to the end. You sit there and you try to work backwards, okay? At this point, we only have alkyl halides. You can see how this is going to be a much more complicated process the more functional groups we learn about, right? So get started here. Let's make sure we got it down. It shouldn't be too bad for this chapter, but it's going to build from here as, you know, you might be able to predict just based on the fact that we're going to start learning about more functional groups. Okay, so let's just go through an example. Here we want to make this particular ether. Well, how are we going to do that? Well, again, in this particular chapter, thinking that you're going to have to start with an alkyl halide is probably a good starting point because that's the only functional group we know, right? But importantly, right, we want to figure out, well, what bonds do we know how to make? What bonds do we know how, what bonds in our target molecule would we know how to make given other molecules, right? So in this case here, we know that we can make these oxygen-carbon bonds through SN2 type reactions, right? So for example, if we started out with an alkyl halide and then we tossed in an alkoxide, in this case an ethoxide, we would be able to form that product through an SN2 type reaction, okay? How do we know it was going to be SN2 instead of like SN1, for example? Well, how highly substituted is that carbon, right? If this was a tertiary carbon, then all of a sudden we would have a different consideration to make, but it's not. It's only got one other carbon bond, so and that's how we would know it would be SN2. Notice that we could have picked another set of reagents and it would have worked perfectly fine. If instead I had decided that this was the bond that I wanted to form here. We could do the exact same thing using a different alkoxide and a different alkyl halide. So these aren't always problems that have just one right answer. There may be multiple ways to do that, okay? And if we were in the lab, we would consider all these ways and we would think about, well, which one's the easiest, which one's the cheapest is a big consideration in the lab that we don't really have in pencil and paper. But nonetheless, sort of work backwards. And again, now it's starting out with an alkyl halide is a really good guess, but of course things will get more difficult as we progress. So then the last thing you want to do is just sort of like double check your work, make sure that what you've proposed is legitimate, thinking kind of in the forward direction now, right? Kind of like a guess and check kind of thing. So with our proposed substrate and our proposed reagent, will these undergo the substitution reaction that we want? Well, we have a primary alkyl halide, so yes, that one's good for SN2, awesome. And then we have a strong sterically unhindered nucleophile, so that's also good, right? So just to double check. And then you simply write your reaction in the forward direction, set up your reaction. Here, another consideration, well, if we're doing an SN2 reaction, then we might as well use this polar aprotic solvent like DMSO, because we know that that's good for SN2 reactions. All right, so then, another example, we can obviously this is going to be part of the assignment after this, is just to go through all these different considerations. One more example here. If this is my target substrate. I know I'm going to need to use an alkyl halide of sorts, but what is that going to look like and what's my other reagent going to be? Again, which one of these bonds do we know how to form? Right? Do we know how to form the bond between a carbonyl and an oxygen, carbonyl carbon and an oxygen? So, right, something like this is not a substrate that we've worked with, so we don't know how to use that. What about this bond here? Again, haven't really talked about these carbonyl reactions yet, so that's not going to do it. But over here, we would. And so this would be working backwards. We know that these, what are called carboxylate ions, are good nucleophiles. So I could start out with one of those. And then, how many carbons? 1, 2, 1, 2. If I had an alkyl halide, remember these are strong nucleophiles but weak bases, which is great because that favors SN2 reactions. And that would get me to my particular reagent. So then again, how I would complete this, you know, if this was on an exam, my final answer would be, here's my carboxylate ion. You can put that counter ion there too. If you left it off, I wouldn't be offended by it, but the book is pretty good about using that. And then your alkyl halide. That would get us to our product here. And then again, is there any sort of solvent considerations that I could make? Well, if it's an SN2, might as well use DMSO or a polar aprotic solvent. Okay, so this idea of a synthetic chemist's job is to start with this target molecule that they want and work backwards to figure out how to create it.